Okay, we are going to do the in-class example I got asked to. We will just quickly run through this. So the first question, which I did not fully read when I was showing this, was that first make a variable that shows production by land use. Now, production by land use. Production by land use. I think actually what I did in class was I took this divided by that. And I actually think what I really wanted was production by millions of acres, which will give you a slightly higher 12 yield. The graph will look very similar. The results are going to be similar because we're all just kind of using this as a transformation of the original data. But this number right here, 12.29, you can now interpret it as for every acre of land, you're producing about 12 million bushels of whatever the product is. Okay, so we got that. We're going to do an exponential smoothing with a dampening factor of 0.9 and 0.1. Smoothing D.1 and smoothing D.9. Right here. Data analysis. We're going to do exponential smoothing. So we have our row from earlier today in class. We're going to move this over here. I'm going to put this out. I'm still coughing. I'm so sorry. And we're also going to do this exponential smoothing here. We're going to move this to 9. And we need to move this over to this new cell and hit OK. So now we have our smoothing and our dampening factors of 0.1 and 0.9. We're doing moving averages. And we're going to put it in here. Moving averages there. And we have 10 already. This is 10 representing 1 decade. Oh, I should say that I'm doing this actually from basic memory from earlier today. But the second question is, well, you can explain what it is, but here's the second question. Create a moving average using the interval of a decade. Now we're going to create a line graph for all 3 of these. And I think when I notice this, I almost feel like I might need to move these down 1 just because of the fact that it's not predicting all the way out, but maybe I'll look into that for next class. So here's our graph, our graphical representation, producing land use. We can see that same kind of graph. Here is just different magnitudes. We can actually fix this bottom part where it's, the 1, 2 for 105 years. You can actually fix that by telling it this is your x-axis. So let's go back up and look. Yep, there we go. Producing land in US. Why is it US? It's supposed to be land use. Okay, so we have years. We have production, blue. We can barely see it now. Smoothing, D.1. We have smoothing, D.9. The D.9 is more of a flat line. The moving average hovers and has more variation than the smoothing does at the 0.9. So now we're going to look at which one is over predicting the most by calculating the mean forecast error for each, which is you would calculate the mean forecast error by taking the actual true value, which is our production land, which is underneath this guy. Yeah, there we go. We take our production land use, minus out. Oh, whoopsie, I didn't want to do that. Minus out the smoothed or predicted forecast through the smoothing dampening factors of each one of these. Of course, this is going to return us N1 because there's N1 or NA right here, or yeah, it's gonna, there's nothing there, so it's gonna produce an NA value. We want to move this all the way down. So what we're gonna do is put a $ for this guy, and then minus out this. Okay. Oh, that is not what I meant to do. Here we go. $. This just makes it easier on us, right? Because that creates a wonderful there. So do dampening factor 0.1. Move this over. This will be for 0.2. No, not for 0.2. We want it for 0.9. Because we put this $D2 minus E2, we can now move it over like so and do the same thing here. Click this button and it drags it all the way down. Then we can do average or moving average. And the same thing for this guy. Ta-da. Okay, here we go. That's our information. We are interested in looking at the average error term across our entire predicted set. What does it say? Very small here, very small here. When we move it over here, we have to adjust this because there are all these NA values. So when we go down, this is, you can see here, it's I don't know if you can see it, but it is row 11. So you can move this, change this into 11, and we could see the same type of answer we got in class now with the actual following of the instruction, but the process exactly the same. We have really small errors for the one that looks exactly like our actual data, right? This one, of course, would have the least amount of errors because it's like basically on top of the actual true value. The next one is of our smoothing error. It actually has a little bit more of fluctuation, whereas our dampening of 0.9 had the largest error because it's just almost trying to, it's basically faking to be almost a linear fit with some kind of little variation in it, with some exponential smoothing occurring. And that's essentially how you would do this. So when you ask for each one, and did they over or underestimate, all of them overestimated. The the lowest error was produced by the smallest dampening error, where the highest was the highest dampening error. And that is the example. And, oh, that's not what I want. This guy. That is that.